So dear students, B.B. Roy of Great Britain had a very good wife. That's where we stopped in last class with a lot of gold and silver. Fine. Now we need to study application of this. Let us consider that there is a resistor with the color codes like this: 1, 2, 3 and 4. First band, second band, third band, fourth band. Assume that the first band had a orange color, the second one has red color, and the third one is yellow color, and the fourth one is gold color. What is its resistance? What to do? First of all, see orange color. What is the value of orange? Orange stands for 3. So write 3. Second one is red color. Red color is how much? 2. Write 2. Then multiplier. Third one is multiplier. Yellow stands for 4. So you should be writing 10 to the power 4. Yellow 10 to the power 4. Then you should write the variation plus or minus. G. I told you G is gold because there are different G. Green, grey and gold. So I should say gold. Gold color represents, see, if gold color comes, I told you gold color can come third place or fourth place. If gold comes in the fourth place, tolerance, that has got a plus or minus 5% tolerance. So the value will vary only by plus or minus 5%. I think it's okay. All right. Now, how to represent 4700 ohm with the least sensitivity to temperature? 4700 ohm with least sensitivity to temperature. Least sensitivity to temperature means its value should not vary much. We can see here 20% tolerance means there is a large variation, 10% means less variation, 5% is least variation. So this should be expressed plus or minus 5%. And how to do that one? 4 color yellow. So first color should be yellow. 7 violet. Second color should be violet. So we have 4, 7 into 10 to the power 2 is what you want. Plus or minus 5%. So the multiplier is 10 to the power 2. What is 10 to the power 2? That is red color. Red. Then plus or minus 5% should be equal to gold. So this is the color code that we can use for representing this value. Okay. Now assume that one student got a resistor, then observed the color code, and the color codes were written down in paper: gold, red, yellow. What is the resistance? Gold, red, yellow. Now you should know that gold cannot come in the first digit place, gold cannot come in the second digit place, gold can come only in the third and the fourth place. So what could have gone wrong with the student? The student held the resistor in the reverse order. Instead of keeping, so what should be the way of holding it? It should be held with the 3 bands close by and the fourth one to the right side. But this student unknowingly did the reverse. So this could have been the problem. That's why gold came here, then red and yellow. So what should have been the reverse order? You just flip it. Then you'll get this color as yellow, this color as red, this is gold, and the last one is also gold. This is the correct order. So the order is reversed. So if it is a correct order, what should be yellow? Yellow has a value 4, red has a value 2, and the multiplier value is gold. When gold comes in the multiplier section, that is 10 to the power minus 1. So into 10 to the power minus 1 plus or minus gold come in the tolerance, that's again 5%. So this is actually 4.2 ohm plus or minus 5% tolerance. I think these three examples will enable you to do all questions on color coding. It won't be much difficult, but this question asked in I think it was asked in NEET examination or JEE Mains, I am not very sure, but this has got something different. A carbon resistor 47 plus or minus 4.7 kilo ohm. See, percentage is not given. You should represent that in different colors. Do this, give me the answer in the comment box. We will discuss in the next class. Now we have to study a little more detail of resistivity and its relation with the temperature. This is given in sufficient detail in NCERT textbook. This is important for your board theory examination because a lot of questions can come from this. In the entrance section, of course, you can expect theory question based on this, variation graphs, all those things. Fine. Now, the equation for resistivity, we proved that it is m by Ne square tau, where m is the mass of electron, n is the number density, E is the charge of electron, tau is the average relaxation time. Now we know that mass and charge of the electron are always constants. So the resistivity will depend on what factors. If m and E square are constant, then resistivity should be inversely proportional to 1 by n tau. That's it. Now n and tau, how do they vary with temperature? We know tau is the average time between collisions. Okay. So when temperature increases, what happens? When temperature increases, two things will happen. One, the speed of the electron will increase, the thermal speed will increase. Okay. So when the thermal speed increases, the probability of collision will increase. Second thing, the atoms, the ions in the solid, they will start vibrating with a larger amplitude, reducing space between them. Due to reduction in the space and increase in the speed, the number of collision will increase. Average speed of the electron will increase, number of collisions will increase. When number of collision increases, the time between collision will decrease. Getting the point? Temperature increases, speed of the electron increases, collisions will increase, and the time between collision will decrease. So we can say tau decreases with increase in temperature. When temperature increases, tau will decrease. First point. Second point, when temperature increases, what about number density of electron? See, the free electrons are generated by absorbing thermal energy. So when temperature increases, available thermal energy increases. When thermal energy increases, more and more electron will become free. So when temperature increases, the number density increases. So these are two different opposite kind of change. If you increase temperature, relaxation time will decrease, but the number density will increase. This is putting us in a very confusing situation because this is inversely proportional to n and tau. So when temperature increases, n will increase, so rho should decrease, but tau will decrease, so rho should increase. There is opposite variations. So how do we tackle this? In the case of metals, we saw the number density is something like 10 to the power 29. So the number density is very high. So we can say in case of metal, mostly electrons are almost saturated. You have a larger number of free electron. Any increase in temperature, of course, will increase the number density, but the percentage will be less. The percentage variation in the number density of electron in a metal will be less. So we can say like this, in metals, increase in n is small, but decrease in tau is large. Understand? In the case of metals, when temperature increases, number density will increase, relaxation time will decrease. But if you see the percentage increase in number density and the percentage decrease in tau, then tau will win. The percentage decrease in tau will be more. So effect of tau will be reflected in resistivity, and we know rho is equal to m by Ne square tau. In the case of metal, the change in n is negligible, but change in tau is considerable. So tau decreases, resistivity increases. Therefore, resistivity of metal increases with the increase in temperature. What does that mean? when temperature increases, the ability to conduct will decrease. The conductor will become less conducting. Hope it's clear. It's given in NCERT, read that one. It's comparison of two things. One, how much does N change and how much does tau change. In metal, change in tau is more than change in N. In semiconductors and insulators, called the non-metals, call it them as non-metals. I think there is some edit here. Yeah, I think this should be edited. I'm sorry for that. This should be edited. Okay. In semiconductors, you should read it like in semiconductors and insulators, it is opposite. Change in N is more, because in a semiconductor or insulator, number density is less. So when temperature increases, you get more and more number of electrons. As the number density is less, the collision is less. So effect of tau is small, effect of N is large. So in a semiconductor, the percentage increase in N will be larger than the percentage decrease in tau. So effect of N will be reflected. So in metal, effect of tau was important, but in semiconductor and insulator, effect of N is important. So when N increases, resistivity will decrease. This implies rho decreases with the increase in temperature. Okay. So two kind of variation. In a metal, resistivity will increase with increase in temperature. In non-metal, resistivity will decrease with the increase in temperature. Okay, so resistivity of a semiconductor increases with the increase in, sorry, there is again an edit here. Here, resistivity of a semiconductor should be decreasing. Okay, I am sorry for that editing here. Okay, decreases with the increase in temperature. That means a semiconductor will become more conducting. This part is correct. Here, metal will become less conducting with increase in temperature, but a semiconductor will become more conducting with the temperature. So when you increase temperature, what happens? Metal will not conduct much, but a semiconductor will conduct better. This part was asked in one entrance examination. A piece of copper and another piece of germanium are heated. Resistivity, what happens to resistivity? You should know copper is a conductor, a metal. Germanium is a semiconductor, non-metal. Okay. Germanium is semiconductor, copper is a metal. So when temperature is increased by heating, resistivity of copper will increase and resistivity of germanium should decrease. So resistivity of copper increases, germanium decreases. That is answer. I hope this part is clear. Now from here, we are going to mathematically relate these things. This is something similar to what you studied in linear expansion in thermal properties. Okay, that's what we have to study. Variation of resistivity with the temperature. Resistivity of a metallic conductor depends on the temperature through this equation. I tell you, you don't have to study the whole equation. I'll tell you why. Rho stands for resistivity. Rho at a temperature T equal to rho at a temperature called T0 into 1 plus alpha into T minus T0 plus beta into T minus T0 whole square. Alpha and beta are temperature coefficient of resistivity. Say temperature coefficient of resistivity. Okay. But all your questions will be based on small ranges of temperature. So when temperature range is small, this T minus T0 square will be negligible. So we will take only the first two terms, rho 0 into 1 plus alpha into T minus T0. You studied similar equation in expansion of length, right? L equal to L into 1 plus alpha delta T studied. This T minus T0 is the difference in temperature, the change in temperature delta T. So you can see rho T stands for resistivity at a temperature T and rho 0 stands for resistivity at a temperature T0, and this T0 initial temperature is normally taken as 0 degrees Celsius. Okay, I will explain it. Alpha is the temperature coefficient of resistivity and its SI unit is K inverse, but you will be using this in degree Celsius inverse because change in temperature in Kelvin is equal to change in temperature in Celsius. SI unit is this, but you will not use that one. So what is the relation between resistivity at a temperature and resistivity at a reference temperature? This is the relation. Fine. Now, for metals, the difference I'll tell you. What is difference? For metals, this temperature coefficient of resistivity is large and positive. Alpha is large and positive. Resistivity increases non-linearly. This is important. The increase is non-linear. For non-metals like semiconductor and insulators, this alpha is large but negative. That means when temperature increases, resistivity will decrease. That means in this equation, this will become minus sign. So there will be a decrease in here. For alloys, the temperature coefficient of resistivity is very small and positive. That means this second part will become negligible. So resistivity will remain almost a constant. So these are the variation. For metals, alpha is positive and large. Non-metal is negative and large. For alloys, it is small and positive. So resistivity changes only very slightly for an alloy, like manganese or nichrome. That's why we use these things to make rheostats, resistances, everything that we use. We call them as standard resistances in the laboratory. You might have done that experiment of Ohm's law. We use a wire, and that wire is normally made of nichrome because its resistance will not change with the temperature, not much. This point was there in grade 10 also. We saw today in the previous class that we have two kind of resistors. The wire wound resistors are made of alloys just because of this reason. Okay. Now NCERT gives you graphical representation of all these ideas. This is the resistivity of copper. You can see that resistivity is small. As temperature increases, resistivity increases non-linearly. There is an increase in the resistivity. But for semiconductor, there is a decrease in the resistivity as the temperature increases. So we can say here the temperature coefficient of resistivity alpha is positive. Here it is negative. But for a alloy, it is positive but small. You can see the slope of the graph is not constant. Here again the slope is not constant, but here the slope is constant. Okay. Now we studied variation of resistivity with temperature. Now this is variation of resistance with temperature, because we know resistance is given by rho into L by A. If you neglect variation in length and area due to temperature, that means the expansion is neglected, then definitely R and rho are directly related. We already know that resistivity at a higher temperature is given by the equation rho 0 into 1 plus alpha into T minus T0. So you can apply the same equation because R is proportional to rho. So we can write resistance at a temperature T is nothing but R0 into 1 plus alpha into T minus T0. You can even write like RT equal to R0 into 1 plus alpha delta T. See, while preparing the slide, there is some error here. This should be read as resistance. This should be also read as resistance. Other than that, there is no change. Alpha is the temperature coefficient of resistivity, or sometimes we call it as temperature coefficient of resistance. Either way, that's correct. Okay. Now, the equation is this. But there is a problem. The problem is the calculations. When it comes to numerical calculations, you will get totally confused. The reason is that this temperature coefficient of resistance is not a constant because it depends on the slope of this line. The slope is not a constant, so alpha is not a constant. Alpha depends on the temperature. See, alpha of copper at 0 degrees Celsius is not equal to alpha of copper at 50 or 100. Alpha depends on the temperature. So you can't take a single value for alpha. But most of our questions take a single value for alpha. That can confuse you. That's why we have, like for IIT JEE examinations, you have to know that alpha is defined through a differential term. Alpha is defined as the fractional change in resistance per unit change in temperature. So alpha is defined around a given temperature. around a given temperature. Say at 300 Kelvin, what is alpha? At 300 Kelvin, alpha is 1 by r dr by dt. So that actually depends on the slope of that line at a particular point. But many times you will be given two temperatures like 30 degrees Celsius and 50 degrees Celsius. Then you can average it over that period. Okay. Now assume that you have a conductor. You have a conductor whose resistance is R0 at reference temperature T0. Okay. Then you can write resistance R1, that means at a higher temperature. It can be written as R0 into 1 plus alpha bracket T1 minus T0. So this stands for resistance at T1. Similarly, resistance at temperature T2 will be written as R0 into 1 plus alpha into T2 minus 0 bracket. You take the ratio, you will get R1 by R2. R0 will cancel. You will get 1 plus alpha times T1 minus T0 by 1 plus alpha into T2 minus T0. But I told you T0 is generally taken as 0 degrees Celsius. So if you substitute T0 equal to 0 and rework on it, you can find out alpha as R2 minus R1 divided by R1 T2 minus R2 T1. But be careful, this is defined around 0 degrees Celsius. Okay. So when T0 equal to 0 degrees Celsius, you can use this equation. More on resistivity and resistance in the later sections. Okay. This part can be little confusing, but be careful about where this alpha is defined around. If it is around a temperature, you can do that. If it is an averaged value, then you can go for this. Thank you for your time.